Greetings everyone, this is Mr. Ma, and in this podcast I'm going to do some example problems, number 6 through 8 on the Newton's second law example handout. So this first problem, example number 6, we have a 5 kilogram rock sitting on a scale on the floor of an elevator. The first thing I like to do is kind of get a visual of what's going on so I can draw a force diagram. So I have a 5 kilogram rock, it's sitting on a scale on the floor of an elevator, and I want to identify what forces are acting on the rock itself. And it says if the elevator moves upward, it moves up and it speeds up at a rate of 2.3 meters per second squared. Find the reading on the scale. And so an important piece of information, if you've ever been on an elevator, what you'll realize is that you feel heavier or lighter depending upon where you're at in the elevator. And it turns out that this feeling of weight is called apparent weight, actually depends on how hard the surface underneath of you pushes on you. And so scales don't actually measure weight, they actually measure how much force they're exerting on you. An example might be if you have your neighbor jump on your back and you're standing on a bathroom scale. Clearly the scale is going to read more than you weigh. It's going to read how forcefully it has to push back up on you or whatever's on the scale. It's not going to tell you how much you weigh at that point. Okay, so I'm going to put a little note on here that scales are going to, they don't tell us your weight. Okay, they don't tell us weight, but they do tell you the normal force, okay, because when you stand on a scale you scrunch up against it, the normal force they exert on you. So let's take a step back. So we've got I'm going to draw a little force diagram for my rock. Okay, we've got a force of gravity. It says it's moving upward and speeding up. So if it's moving upward, my velocity is positive, and if we're speeding up, then we're accelerating. And the direction of the acceleration, or its sign, because it's speeding up, is going to be the same as the velocity. So I'm going to go ahead and draw my acceleration. It's going to be in the upward direction. So we're trying to find what the scale reads. In other words, we're trying to find the normal force of the scale. And so I'm going to use Newton's second law whenever it's asking me for a force. And I have this problem that's going to be dealing with multiple forces. I'm going to need to use Newton's second law, which involves the net force. So F net is equal to ma. We're going to go ahead and say that helping me accelerate upward is the normal force, minus what's hindering me from accelerating upward, which would be the force of gravity. That's equal to ma. So I've got help minus hinder ma. I just want you to take note of that the fact that I had this upward acceleration, it guided my help minus hinder setup. Okay, so now I know my help minus hinder is equal to ma. So we're trying to find the normal force. The force of gravity is just going to be the mass times the acceleration due to gravity, which is mass of 5, acceleration is 9.8, and so we're looking at a 45 Newton rock. That's the weight of the rock, how much force the Earth is exerting on it. So we're going to put 49 is equal to mass times acceleration. We've got 5 times 2.3 meters per second squared. That was given in the problem. And so what I can do then, the normal force minus 49 is equal to 11.5, which means that the normal force is equal to 60.5 newtons. Now, if I'm on the bathroom scale and I start to speed up, we notice that we feel heavier. And so this apparent weight that we feel heavier is due to the fact that the ground underneath of us has to actually push on us harder than the normal 49 newtons we would feel if we were at rest. So we feel heavier because the ground pushes us more. And so this apparent weight makes us feel heavier because that supporting force is greater than my weight force. All right, so the next step, it says now the elevator moves upward while slowing. So we're still moving up, but we're slowing down now, okay? So if we're slowing down, then the acceleration is going to have to be opposite the sign of my velocity. And so we've got 2.3 meters per second squared. Find the new reading on the scale. So my acceleration is down, and because it's accelerating downward, I know the downward forces are going to be greater than the upward forces. Force normal. We're trying to find that new reading. Now, the weight doesn't change. In other words, the Earth doesn't pull any less than it did a second ago. So the force of gravity is still 49 newtons. We still have the same weight, but we have a different scale. The scale is going to push differently on us in this situation. So when I do my acceleration is 2.3 meters per second squared. What I'm going to do now, and you can totally do this, is I'm going to make the downward direction positive. And by doing this, I'm going to change my help minus hinder setup. Okay, so this downward acceleration is going to lead me to change my help minus hinder setup. So I'm going to define the downward direction to be positive. That means that my acceleration down there is positive. So when I do Newton's second law, the net force is equal to mass times acceleration. I'm going to make everything down be positive. So helping me accelerate in this problem is the force of gravity. Hindering me from acceleration is actually that normal force, and I can set that equal to ma. So I've got 49 newtons minus whatever the scale reads is equal to the mass of 5 times that acceleration of 2.3. 49 minus Fn is equal to 11.5. And so now we'll notice that when I get my get 49 to the other side and divide both sides by -1, we're going to get the normal force now is less than what it was when I was just on the scale normally. And now the scale actually reads 37.5 newtons. So when this supporting force is less than our weight, then we actually feel lighter. We kind of feel this light, weightless feeling as the scale kind of is not pushing as hard as it used to. So there we have it. All right, the next question, part C, says now the elevator is moving downward while speeding up. Downward while speeding up. So it's accelerating. It's moving downward, so velocity's down. The acceleration is going to be the same sign. Okay, so they're both negative. So we've got we're looking for what the scale reads again, the normal force. Acceleration is downward, Fg is equal to 49 newtons. And what we're going to see is that if the acceleration is 2.3 meters per second squared, and it's still down, it's still accelerating down. So we just did this problem where it was accelerating down at 2.3 meters per second squared. It's the same as part B, which is 37.5 newtons. Okay, so what this means is that when I look back at that problem and I think about when I actually ride an elevator, we feel that kind of like lighter than our lighter feeling, that we feel like we don't weigh as much, whenever 2 times in the elevator. It actually occurs twice. So when we move downward and speeding up, we feel a little bit lighter. The scale doesn't push quite as hard. It's only going to be pushing 37.5 newtons. So that will occur at 2 points on an elevator, depending upon whether we're speeding up and then which direction we're moving. All right, these last couple questions are going to be involving a couple different problems where we're going to apply this information. So example 7 says a fisherman pulls vertically out of the water, a fish vertically, with an acceleration of 2.5 meters per second squared while using very light fishing line. It has a breaking strength of 22 newtons. Unfortunately, the line snaps under these conditions. What do you know about the mass of the fish? All right, so I see acceleration, a force is being applied, and it's asking about mass. So this is screaming Newton's second law to me. So if I look at my little fish here, he's got a little hook on here, and we're trying to pull him out of the water. I look at the forces on my fish. We've got a force of gravity, and then we've got this tension from this string, and I know it's accelerating upward at 2.5 meters per second squared. So when I play this help minus hinder game, I'm trying to find the mass of the fish. So right now I just kind of remember, okay, Fg I know is just the mass times the acceleration due to gravity. And so helping me, net force is equal to ma. My net force is help minus hinder. Helping me accelerate is the tension. Hindering my acceleration is the force of gravity. It's equal to ma. But I still don't know the mass yet. Okay, so notice I'm still kind of missing. I'm missing the mass here. So I'm going to rewrite this. The force of tension. I know that the string broke, and the maximum tension the string can even withstand is 22 newtons. So anything less, it wouldn't break. So it's got to be at least 22. And then in terms of Fg, I don't actually have the mass, but I know that it's equal to mg. So m times 9.8 is equal to m times a. And so right here, this is a little arrow. I just want you to notice that I still have an unknown. Actually, we know the acceleration. Let me get rid of that too. Acceleration was 2.5. Now I have m. I was missing it on both sides, but now when I plug this into Newton's second law, now we have m on both sides. So what I can do then is I can get some like terms together. 22 is equal to 12.3 m, and then we're going to get a mass of 1.8 kilograms. Now, the fish has got to be at least 1.8 kilograms because that's what would cause the tension of 22 newtons. But the fish could have even been more than this, because if it was more than that, it would obviously break the string as well. So we can actually use Newton's second law to find other unknowns, like the mass, which showed up in both sides of this equation, and we could actually solve for it in that way. All right, we've got one more example. So number 8, it says an upward tension force pulls on an object with a force equal to 1/3 of the object's weight. So I'm going to go ahead and draw a little force diagram here. It says we've got a tension force that is 1/3 of the object's weight. Okay, so it doesn't actually give me any information about mass. It doesn't even give me any values. It just gives me this kind of ratio. So I'm going to go ahead and I need to find the acceleration, but I'm not actually given anything but what I know here. But before I get too discouraged, the force of gravity is equal to mg, and that is the weight. I mean, that's what I mean by force of gravity. So if it's 1/3 of the object's weight is the amount of tension, I'm just going to plug in 1/3 of the weight, which is 1/3 mg. And if that's the case, I know it's going to be accelerating in the downward direction. So I'm going to play Newton's second law, help minus hinder equals ma, helping me accelerate in the downward direction, which I'm going to choose to be my positive direction, is going to be my force of gravity minus the force of tension is equal to ma. Now I'm going to substitute in what these values are equal to. So the force of gravity was just mg minus 1/3 mg is equal to ma. And now what happens is I see a like term of mass in every single term. So if I were to actually divide both sides by m, what will happen is that I can simplify this into a much simpler expression. For mass, it doesn't matter if I don't know the mass. And so once I get to this point, g minus 1/3 g, that's just 2/3 g, which is 9.8. It's going to be equal to a. Our acceleration is going to be 2/3 g, which is 6.53 meters per second squared. Beautiful. Okay, so it felt weird because I didn't know mass. But if the tension force is a third of Fg, okay, we could set up with a bunch of m's in my equation, and they canceled. Okay, there's a little side note there. All right, so this has been examples 6 through 8, and I hope that this has been helpful.